think several of you are looking for the sign-in sheet, and I think, Lingyi, is that what you have right there? Is that the sign-in sheet? Oh, yes. Yeah, so if you're looking to sign in, Lingyi's got the sheet up there. I think a few people are looking for it. You're fine, take your time. You think we should get started? Yeah, get started. All right. All right. So today is our last day that you have to put up with me. So congratulations on making it this far. Today we are going to design our own patient-level prediction study, and we're going to write a paper with Bonnie. And that is our goal, is to produce results that we think should belong in a medical journal. And that's our goal today. So this morning, I'm going to talk about the other pieces of designing a patient-level prediction study and how you can use the results of a prediction study in your clinical practice and in your research. We'll talk about what you can and what you cannot do with a prediction model. And then this afternoon, we will actually show you how to implement that patient-level prediction study using the Atlas tool. We will run that analysis against databases, and we will write a paper. So that is our goal for today. I think I still have a job. So we are talking about 3 different types of analyses that we can do. And all of today is going to focus on patient-level prediction. So trying to answer the question, amongst a target population, which of those patients will go on to have some sort of an outcome. So yes, the last 2 days we talked about the 3 different types of studies. Today we're going to exclusively focus on prediction. So I want to provide an example of a prediction that, a way for you to think about prediction problems that might be important for you. Let's imagine the following situation. There's a disease in the world that is fairly common. So about 100 cases per 100,000 person years. And people have a lifetime risk between 5 and 13%. So that's a disease that happens pretty regularly in a population. And you don't want to have this disease. If you were to get this disease, then you have a bad chance of comorbid problems. However, recent technologies have advanced so that we have at least decreased the chance that you will die due to this disease over time. But the reason why there might be value in doing prediction is because the earlier you can find the disease, the higher the likelihood is that any treatment you would use would be effective. So the motivation for doing a prediction study is that if we could predict who is going to develop the disease, we might be able to treat that patient earlier and they might have better outcomes as a result. So that's a hypothetical situation that I want you to think about. So how would a prediction model work in practice? Well, you would have a population of people who are at risk of the disease. Think of that like your target cohort. And you would apply this prediction model to all of those people in your target population. And the model would tell you that some people are predicted to have the disease and some people are not predicted to have the disease. And so it's taking all of the people who are at risk and it's splitting them into two groups, those that are at high risk and those that are at low risk. So that's how a model would work. Now, the opportunity of applying a model like this is that for those patients who are predicted to have the disease, we might be able to do something for those patients. We might be able to treat them or monitor them more closely or otherwise just intervene on those patients to try to prevent the outcomes of the disease from happening. But the challenge with using any prediction model is that prediction is not perfect. We cannot guarantee that we will find the right people who definitely have the disease and not find the people who don't have the disease. So imagine that this model for this disease I'm describing has the following characteristics. 10% of the people who are predicted to have the disease are false positives, meaning we say that they're going to have the disease, but they do not actually have the disease. So 1 in 10 of the people that we predict is wrong. This model might also have false negatives. And here we're saying a 20% false negative rate, meaning that some of the people will be told that they are not going to develop the disease, but that's wrong. They will develop the disease. And so for a false positive, the concern is that we tell a person that they're going to have a disease, and that person has to worry about it. They might get extra treatments that they didn't need. So that would be bad for a false positive. But a false negative is also bad because you're going to tell a person that they are safe from the disease when they're not. And that person might, as a result, not take care of themselves as well as they should, or not go back to the doctor, or delay their treatment. So it's quite bad to have a false positive and false negative. And this model that I'm describing has a 10% false positive rate and a 20% false negative rate. The other challenge with this model is that it is not something that is easily interpreted by the non-expert. It's a model where you have to have a lot of knowledge to be able to interpret the results and understand how to use it. And the results are uncertain, so we don't know whether or not we can be sure that using this model is always giving us good answers. So my question to you is, if I gave you a model for a common disease that's very serious, and this model had these characteristics, that it generated a 10% false positive and a 20% false negative, do you think we should use this model in clinical practice? I want you to stand up if you do think we should use this model in clinical practice. Okay. And I want you to stay seated but wave your hands if you think we should not use this model. Does anybody think we should not use this model? Okay. A couple people think we should not, and those that are standing think that we should. Okay.
I don't know, Patrick.
So I don't know those of you who are not standing up whether you really think that it should not, but I'm going to assume that you are. I'm going to say that in this room right now, it looks like half of you think we should use the model, and half of you think we should not use this model. Is that fair? All right, so you guys can sit down. So I'm talking about prediction models in general, but I'm actually talking about something that's used in clinical practice every single day right now. Screening mammography for breast cancer is an example of a prediction model. Women who are at risk of getting breast cancer may undergo a screening breast mammography, which is something that is recommended to be done every few years for women to try to detect breast cancer early. And this is a model because it is not a definitive definition of a particular disease. It's an image that serves as this black box, a proxy for what the real disease is. And it turns out that doing a screening mammography gets you 10% false positives and 20% false negatives, meaning some women are told that they might have breast cancer when they don't, and some women are told they don't have breast cancer when they do. Yet it is, in many developed countries, it is now accepted clinical guidelines that we think using this prediction model is a good thing to help patients, despite the fact that it has performance characteristics that are far from perfect. Now, what's interesting is that screening mammography for breast cancer is something that we have been doing in many countries for over 20 years. It's very common practice for women's health. But even just 2 months ago, the US Food and Drug Administration had to issue an advisory about the use of screening breast mammographies. And it turns out that one of the biggest uncertainties in using a screening mammography is that if a woman has dense breast tissue, we know that the model, the mammography, the imaging technology, works less effectively. So if you do not have dense breast tissue, we know how the model works. But if you do have dense breast tissue, we don't really know whether we can trust the results. And so just a couple months ago, the US FDA had to issue a warning recommending that when you look at your results from a screening breast mammography, you need to look at what is the measurement of breast tissue density, because that tells you how much you can trust the results from the prediction model. So this is a prediction model that we have been using around the world for 20 years that has imperfect operating characteristics and uncertain results. Yet we have decided as a healthcare community that the benefits of performing this prediction model outweigh the risks of using it. And I share this example because what we are now going to be doing today, and hopefully many of you will be interested in developing other prediction problems, is the same thing as inventing a screening mammography. But instead of us having to build a machine to take a picture of a breast, what we're going to do is we're going to write an algorithm that looks into data to try to predict which patients get outcomes and which ones don't. And if our algorithms can perform as well as a screening mammography at telling women which women are going to get breast cancer and which ones aren't, then it's my opinion that every doctor should be using our algorithms just like every doctor uses a screening mammography. So in case I haven't convinced you yet, let's walk through how a prediction model can be used. What I'm showing you here is a picture of 1,000 people. Each one of those little icons is a person. And so this is 1,000 different people. Now let's imagine that 10% of those people will experience some outcome in the future. I've colored those in red. So 10% will get the outcome, and 90% are in black, will not get the outcome. If we do not have a prediction model, then the only appropriate thing we can do as doctors is treat all patients equally. We're going to do the same thing for every single patient because we don't know how to do things differently for different patients. So without predictive modeling, every person in this database has to be assumed to have a 10% risk of the outcome. And it's like they're randomly scattered in that group. So nobody has a 100% chance of the outcome, and nobody has a 0% chance of the outcome. Instead, everybody has a 10% chance. And the reason why I can't treat patients differently is because I know nothing about their individual risks. So I must behave as a doctor as if everybody has this 10% chance. And if I think that someone has a 10% chance of an outcome, I have to make a decision. Do I treat everybody because everyone has a 10% chance? Or do I treat nobody because everyone only has a 10% chance? Those are really my only two options if I'm a doctor, is treat everybody the same way. I either treat everybody and I'm wrong 90% of the time, or I treat nobody and I'm wrong 10% of the time. Those are my only two options as a doctor. So what does a prediction model do? Well, a prediction model produces a probability for every single patient. And that probability represents the risk that that outcome is going to happen. So if I have 1,000 people, I can assign each person their own individual probability. And one way to think about it is that I could rank the 1,000 people from highest probability to lowest probability. And if I could rank the people based on their probability, something interesting happens. Instead of the red dots being randomly scattered across the screen, you now notice that there are more red dots more red people towards the top and less red people towards the bottom. By ranking people on their individual probability of an outcome, we can identify high-risk people and low-risk people. And if I know which people are high risk and I know which people are low risk, I could choose to treat those patients differently. Because people who are at high risk, we might be more aggressive in treating them, and people who are at low risk, we may be more careful in treating them. So now, instead of treating every patient the same, I have the opportunity to treat patients differently. So remember, I said before that everybody had a 10% probability. But if we do predictive modeling, now each person has a different probability. That top person might have an 80% chance of having the event. So very likely. And the second person might have an 81% chance. And the 10th person might have a 65% chance. And I can go all the way down to the 100th person who might have a 40% chance. And the 250th person might have a 27% chance. And I can go all the way down to the last person who might have a 1 in 100,000 chance of the event. Clearly, the way I would choose to treat a person who has a 1 in 100,000 chance of an event is different than the way that I would choose to treat the person who has an 82% chance of the event. But if I don't apply predictive modeling to my problem, I don't know the difference between the person who's an 82% chance and the person who's a 1 in 100,000 chance. By applying our prediction models, even if our prediction models are not perfect, we can start to see how well we can find the high-risk people from the low-risk people. Now, it's important to understand that these models that we are going to produce are not going to be perfect. In fact, they're not going to be very good at all. But our goal is not to produce a perfect model. Our goal is to do better than a world where we have no model. So as long as we can do better than nothing, we are already advancing healthcare. Because if we do nothing, we have to treat everybody the same way. Whether that's treating everybody or treating nobody, we have to treat everybody the same. So long as we can prove that we can produce a prediction model that's just a little bit better than random guessing, then we are improving the way that we can treat patients. So how does this work? If we rank order everybody from high probability to low probability, then we can actually begin to understand how much our model is telling us about our ability to discriminate between the high-risk people and the low-risk people. For example, we could, because we have an individual predicted probability for every patient, we can use that number that comes out as a threshold. And we can use that threshold to say, we will choose to treat everybody above the threshold one way, and we'll choose to treat everybody below the threshold a different way. So in this picture, if I chose to set my threshold at 65%, what you see is that the model is only going to put 10 people into that high-risk group, which means 990 people will be put in the lower risk group. So what is the consequences of that? Well, of the top 10 people, 6 of them actually do have the disease. 4 of those people that we predicted to be high risk did not have the disease. Those are false positives. But of the 990 that were below the threshold, 896 of them were not diseased, and 94 of them were false positives. Some of the statistics that we can use to summarize how well a prediction model works in healthcare are some statistics that I'm showing here. A very common one to discuss is positive predictive value, which sometimes you'll see in papers referred to as precision. And that is the number of true positives divided by the total number of predicted positives. So in this case, it's the 6 out of the 10. That's a 60% positive predictive value. You'll also see, as you look at prediction models in healthcare, that people will report the negative predictive value. So that's the number of true negatives divided by the total number of predictive negatives. So in this case, that's 91%. Other numbers that you will see when we talk about performance of models is sensitivity. So sensitivity is the proportion of people with the disease that you actually find. So here, there were 100 people that actually had the disease. We only identified 6 of them, so that's a 6% sensitivity. And we can also talk about specificity, which is the number of the proportion of mistakes we're making. And here that is 99%. So we're only making 0.4% mistakes. One final measure that I'll just mention is a measure of accuracy. It's basically the number of true positives and the number of true negatives divided by the total number of patients. And so in this case, that is a 90% accuracy. Importantly here, we, the clinicians, the researchers, we get to decide the threshold. So we choose the threshold 65%, and on the basis of that threshold, we can see what the operating characteristics are. So this threshold here, we can see that we do not find very many people in that high-risk group. The majority of the people we find do have the disease, but we're not finding very many of the people with the disease. That's the trade-off that we would have to make. If the intervention that we were considering for people who were high risk was very invasive or very dangerous, then we probably would not want to have a very large number of false positives. So setting the threshold really high might be the responsible thing to do. On the flip side, if our goal is to identify risk for as many people as possible, we might think it's not good enough that we're only finding 6% of the cases. So we can choose, as researchers and as clinicians, to change the threshold to evaluate how well this works. Let's imagine I lower the threshold to 27%. Now I've identified the top 250 people, and I'm calling that my high-risk group. And that means the 750 people below that threshold are my low-risk group. I can use the exact same structure to understand the performance of this prediction model. So now we can see I have 62 true positives, 188 false positives. Excuse me. So now my positive predictive value has dropped. It was 60%, now it's down at 25%. But the trade-off is our sensitivity just went up from 6% to 60%. We can trade off our rules to find more people, but as we find more people, we're probably making more mistakes of false positives. There is no right answer to where you set your threshold. You have to decide where to set the threshold based on the clinical problem that you are interested in solving. But what we would like is that there is some threshold where we think that the combination of the positive predictive value and the sensitivity and the specificity makes us believe that using the model is better than not using a model at all. That doing personalized medicine is a better idea than treating all of the patients equally, whether it be treating all of them the same or not treating them all. Let me just stop there and see if there's any questions. Stand up if this is still making sense. All right. Okay, so it's making sense to most people. Okay, very good. Okay. So, the main point I want to leave you with is our goal is not to produce perfect prediction models. Our goal is to do better than nothing. And so long as we can do a little bit better than nothing, we can actually improve the lives of patients around the world. So many of you are training to become doctors, and so you will be confronted with prediction questions on a daily basis as you are treating your patients. Because what will typically happen is a patient's going to ask you, what's going to happen to me? As a patient myself, that is what I ask my doctor, is what's going to happen to me? And a doctor has 4 options of how they could respond to that. The first is that they could deny their ability to actually predict at an individual patient level and say, I can't tell you what the chance of something happening to you. That will make a patient quite upset. Probably the most common thing that you would see is that the doctor will quote an overall average across all patients. So they might say something like, well, in some published paper, there were 1,000 people and 10% of them had the outcome. So I think your risk is 10% because 10% of a population had the outcome. But of course, he's going to say the same thing to every single patient, that every patient has a 10% risk, and clearly we should be able to do better than that. The other frequent thing that many doctors do is they use their own knowledge and their own experience from whatever patients that they have seen in their past to say, well, for patients who I've experienced who look like you, this is how often I saw this outcome happen. And that might be better than the overall average for the entire population, but it might be worse because most doctors do not see enough patients who look just like the patient in front of them to be able to produce a valid estimate. So that can be a bad or misleading number. It's our assertion that what should be done is that doctors should be able to provide a personalized prediction based on some sort of prediction model. And that prediction model doesn't have to be perfect. It's just got to be better than all of these other options. To do this means that we have to, 1, decide to train a prediction model to answer this question that we think is important. 2, make that model available to clinicians so they know it exists. So that's why we need to publish papers that provide these models to the world. And 3, we need to have some way so that doctors and patients can provide their information about what you know about them, their characteristics like their color and size of the candy. They have to be able to provide that information such that the model can use that information as an input to produce the probability as the output. So the reason why we are presenting for the last week about OHDSI and the OMOP Common Data Model is the OMOP Common Data Model is the tool that makes it possible for the data to be used as an input to these prediction models such that the prediction models can produce the output, which is the predicted probability. So, you all focused on this yesterday. I will just remind you that our goal for all prediction problems is you have a cohort. There is some time zero index. You get to use everything you know about a patient before that moment to predict something that's going to happen to them in the future. And every prediction problem can be simplified into filling out that piece of paper you had yesterday. You just need to be able to define your target cohort, your outcome cohort, your time at risk, and then the model specification is what we're going to talk about today, which is how do we actually apply machine learning algorithms to these observational data to predict which patients in T go on to belong to O in the time at risk. So, what I just described to you was how we use a model. We apply a model to a patient to produce an individual predicted probability. That is the goal. Nowhere did I just describe to you what was inside of the model. Using that screening mammography example, nobody really knows how an imaging machine works, and you have to ask your radiologist to actually interpret the data. So we don't know the machinery there. We just know that once the output comes out, that you can have some understanding of a patient's risk. And in the same way, when we talk about patient-level prediction here, the models we're producing are not for the purposes of explaining why it is that someone's going to develop the outcome. They are purely for the purposes of assigning a predicted probability to an individual. To be more direct about this, the number one mistake that is made by most prediction papers that are published in the literature is that they try to use the model to explain why this phenomenon happens. They try to use the variables, the predictors, to describe risk factors representing the reasons why someone is going to get a higher probability. So I'm going to take a couple minutes to explain why that is not an appropriate thing to use a prediction for, but still to help you understand that we can use this model even though that's not how you will see published papers done. And part of this starts with this idea of the word model. And it turns out, depending on your background, the word model means different things to different types of researchers. In statistics, a model is an idea of something that is used to describe data. It's trying to be an abstraction of the data to represent the data in a way that can characterize it appropriately. Epidemiologists, though, talk about models differently. They talk about models as a tool to test hypotheses about causal inference. And so even though they're both using the word model, those are very, very different things. The statistician is just describing an abstraction of the data, whereas the epidemiologist is using the model to try to test what's happening in the world. The new area of data science is using the word model even differently from that, and this is more akin to how I'm going to describe it, which is you use the data in the past to predict the future. So we don't care whether the model is clinically correct or appropriate. It does not need to represent the data appropriately. It simply needs to allow us to produce a predicted probability for an individual that we can test to prove that that predicted probability in fact is going to get the right answer in the future more times than not. So there is a difference between explanatory modeling, which is when you are interested in answering the question, why is one factor influencing an outcome, from prediction modeling, which does not require an explanation of why. It just becomes a statement of truth that a model can either predict the future or not. Over here, do you guys have casinos? What? Casinos? Okay. Okay. So if you were to go to a casino and you could go to the casino to risk money and hopefully make money, the difference between an explanatory model and a predictive model would be the following. Imagine somebody could give you a black box and you went to the, what game would make sense? You went to the craps table. Is craps a common game? or a roulette wheel. Does people know what a roulette wheel is? It's got like red and black barks, and you spin a. Let's see. Okay.
They're just students and they don't really go.
Yeah. Okay. I'm a degenerate, so it's okay. Okay. Let me try something different. So, if I flip a coin, I don't think I have a coin. Ugh. All right. If I flip a coin, that coin is either going to be heads or tails. And so I have a 50% chance that I'm going to get heads and a 50% chance that I'm going to get a tail. Now, I could ask you all to guess when I flip this coin, is it heads or tails? And probably you're going to get it right 50% of the time because you will be guessing at random whether it's heads or tails. Now imagine that we were to bet money on your guesses. And so I will bet you $10 that it's a head, or I'll bet you $10 that you will guess it correctly, that you will guess heads and it's heads, or you'll guess tails and it's tails. And if I'm right, if your guess is right, I give you $10, and if you're wrong, you give me $10. Because this is a random game, if we kept playing the game of betting on this, we probably would be in the situation where we'd end up with the same amount of money. Because for however many times you got it right, about the same number of times you'd get it wrong. Now imagine I could give you a magical box. This magical box just has a screen on it that says heads or tails. And somehow this magical box, every time it says heads, not every time, when I flip the coin, this thing says heads, and when this says heads, 75% of the time, the coin gets heads. And when this thing says tails, 75% of the time, the coin gets tails. So it is guessing what happens to this coin much better than your random guesses. This magical box that is guessing the coin flip, I have no idea how it works. Just somehow magically, it seems to be getting the answer. Okay. So my question for you is, would you like to buy this magical box even though you don't know how it works, to play this game of betting on money? Who would like to have this? Many people would like to have it, okay? But you don't know how it works. You don't know why it gets the right answer. So why do you still want to have it? Because you want to win? You what? You want to try it. Because it seems like you're going to make a lot of money if you do it, right? Now, so you don't understand how it works, but you still want to try it because it seems like it does the right thing most of the time. In healthcare, particularly in medical doctors, we always want to be able to understand why things are happening. It's built into our nature as researchers that we want to be able to understand why. And it makes good sense. As researchers, we should try to understand why. That's a good thing to do. But even if we can't explain why, if something just works, it could be very profitable. If this thing could guess my coin flips and I was willing to bet $10 on every coin flip, I could make millions and millions of dollars very, very fast. In fact, this example of flipping a coin and having a random black box, this is what the financial industry is doing every single day. They are building algorithms trained on data to guess whether the stock market is going up or down. And they do not know why their models sometimes work. They only need their model to work a little bit better than random guessing. Because if they can just do a little bit better than random guessing, and they can bet a lot of money on every time they flip the coin, then they can make a lot of money. Now, I don't like the idea of betting on patients' health. It seems bad to take a high chance that we're going to do something bad. But remember what the alternative is. The alternative is to treat every patient the same. Treating every patient the same is the same as flipping the coin and guessing heads or tails. So we don't have to be perfect. We just have to have a system that does a little bit better than random guessing. And just like our friends in the financial industry are making lots of money, we could actually help lots of patients. Because on average, we'll do a lot more good than we're going to do harm. Okay. That's not to say that we shouldn't also do research to understand why the magic box works. But what I'm telling you is that those are two different tasks. Understanding why the box works is different than proving that the box works. And what we're going to focus on today is trying to figure out, can we find a box that works? We may or may not understand why, but if it works, then we've got a chance to help patients. Make sense? All right. I think I'm going to skip that. Yeah, I'm just going to skip that. So there is a big difference when you're trying to explain something from when you're trying to predict something. And so I'll just go through a couple of these. This is a paper that was published that we'd like to reference because it's quite useful in explaining the difference between these two tasks. When you're trying to explain something, the goal is to actually test a hypothesis. And more times than not, you're trying to test a causal hypothesis. Now, a pop quiz, we taught you we talked about that there's methods to test causal hypotheses. What do we call that type of method or type of analysis? Estimation. That's right. So the reason we draw a distinction between estimation and prediction is because estimation is a tool to test causal hypotheses. In prediction, the goal is actually just to try to use old data to predict new observations. Now, in an explanatory model, what you typically do is you select the variables that you are interested in to test your hypothesis. So you have an idea that a particular variable is related to another variable, and you select those variables to test your hypothesis. But in prediction, I don't need to decide what variables I want to look at. I told you that in prediction, we can use everything in someone's medical history to try to predict their future. So I don't have to tell the prediction which variables I think might predict the outcome. The data can tell me what things predict that future outcome. When we're doing exploratory modeling, the goal is actually to minimize bias, meaning to produce an estimate that is as close to truth as possible. That's actually not the goal in prediction. In prediction, we're actually trying to minimize both bias and variance. To make it even simpler, I'll say the goal is to maximize our ability to predict the future. And I don't care how I do it. If I can make this magic box get the right answer of heads or tails every single time, I do not care whether I understand this thing. Just as long as it gets me the right answer the most time, I'm happy. So when we think about how to build a model, when we're in the explanatory space, one of the real goals is interpretability. That is, you want to be able to explain what you're seeing and understand the relationships between the variables. The only constraint in prediction is that the predictors that I'll use to predict the outcome, those better be predictors that I will have available to myself when I go to apply the model in the future. And in an explanatory model, when I evaluate a model, there are different statistics that I would use to know whether or not my model did a good job. In prediction, those measures that I just showed you, positive predictive value, sensitivity, specificity, accuracy, those are metrics that tell us how well our prediction model works at the task that we're interested in. Yes?
Can you explain the type 1 and type 2 errors? And because the conception is to abstractly use actual disease example to illustrate this concept.
Yeah, thank you. Good question. So yeah, when we talk about type 1 error and type 2 error, we're talking about false positives and false negatives and how often those happen. And so in the explanatory case, the concern about bias is that you are trying to describe the relationship between two variables, and the bias is that somehow systematically what you are trying to observe, you consistently get the wrong answer for that relationship. But the goal of for explanatory variables is to understand the relationships between variables. So the false positives and the false negatives that we're describing there are false relationships. In the prediction space, think of that as actually producing the predicted probability for every patient. So now I don't care about the relationships between variables. I care about how well I do at separating the people who have the disease from the people who don't. So there, my false positives and my false negatives are not relationships, they're actually individuals. And so the goal when I'm training a model is to make sure that I get the relationships right, whereas the goal when I'm in prediction is to make sure that I classify the patients correctly. Does that make sense? Any other questions? One of the most common phrases that you will see in the medical literature, if you look up something that says prediction, is you'll see this phrase, risk factor. And in the OHDSI community, one of the things we're trying to do is abolish this term, make it go away, because it is actually quite problematic and harmful for using models appropriately. One of the main reasons is because the word risk factor is an ambiguous term. It's not clear what people mean when they say it. And we have many examples where different people using the same term risk factor mean it to be different things. But most importantly, the reason we think this is a bad idea is because a prediction model is not trying to find the variables with the relationships to the outcome. It's trying to be a black box that produces the probability for a given patient. So I don't care what variables go into my black box. I simply care that my black box works. And so in the case of risk factors, what many people are trying to do is describe which variables should go into a model to try to produce the outcome. And if you want to identify which variables you want to put into a model, you can perform estimation to figure that out. You can learn which variables are importantly related. And you could do that by testing causal hypotheses, which is to do an explanatory model. But in prediction, all we are going to do is identify variables that go into this black box that allow us to guess at the predicted probability. If a variable is used in my black box, all it means is that that variable is associated with the outcome. But association does not mean causation. And so the fact that two things happen to co-occur does not mean that one variable causes the outcome. In fact, it could be completely the opposite. So we will be able to see which variables go into our black box, but we should not overinterpret that to be that because they went into the black box, that those must be the quote-unquote risk factors. If your goal is to find causal factors of an effect, you should be doing population level estimation. And take our other tutorial for how to learn to do that. If your goal is to search for the association of an individual parameter, well, you can do that with characterization. Remember yesterday, we characterized the color and the size of our populations, and we observed that, pink people were more likely to take the white pill, and big people were more likely to take the purple pill. Well, that was a characterization that told us about an association. That's totally fair game. But what we're talking about right now is actually to do prediction, so we care about the individual predicted probability for a patient, and the model that we're creating is the way to produce that probability. I'm going to explain this, but I'm not sure how well it'll be useful. Raise your hand if you have seen a regression model, being some sort of a mathematical formula to describe variables together. A couple hands. Okay. Well, for those of you who have, a regression model is a mathematical formula that describes the relationship between variables. And usually you'll see it expressed in this type of a format. If I were to say this in words, your y variable would be your outcome. And what we're saying is the outcome can be predicted by some combination of other variables or predictors, which is here represented by x1 and x2 and x3. Now, when you read most published literature articles, they will report the effect of a particular predictor variable on the outcome. And what they're actually reporting from this formula are these beta coefficients. That is actually an estimate of the relationship between one variable and the outcome conditioned on all other variables. And one of the biggest mistakes that people make when interpreting statistics is that they read that beta coefficient and they think it means something that it does not mean. What happens is this model, the whole formula, is the way that we're able to magically predict the probability for an individual. So that formula is what's inside of the black box. But people like to look at the formula and think that they can gain insights. But here's the problem. If the beta coefficient is equal to 0, you've learned absolutely nothing. You do not know whether that variable is associated. You do not know whether that variable is associated with the outcome, and you certainly cannot make any causal statement. If the beta coefficient is not 0, well, you can make the statement that by being not 0, you know it is associated with the outcome, but you can't make any causal statements about it. You simply know that there's an association. And when the variable is greater than 0, that means that there's a positive association, but only under the assumption that all of the other variables are fixed. And the moment that you have two variables that are correlated to each other, then you do not know how to interpret that beta coefficient. So you absolutely cannot know the causality. And the same thing holds if the beta coefficient is less than 0. What you know is that you have a negative association under the assumption that all other beta coefficients are fixed. But if you have correlated variables, then all bets are off. What this means is when you're looking at a prediction model, no matter what, you know nothing about the causal effects. So please, please, please do not perform a prediction model and interpret the model and then make causal claims. Please don't be one of those people that's like 90% of the medical literature right now, because those papers are just mathematically incorrect. So, given that we can't explain a variable, why is this still valuable? Well, my assertion is that in healthcare, when a patient asks, what's going to happen to me, that question matters a lot more to a patient than why is something going to happen to me. You know, when a patient wants to know what's going to happen to them, they do not need an explanation of the biologic plausibility of all that's going on in their body. They just want to know, am I going to be the person who gets lymph node metastases or not? And so knowing what's the chance that something's going to happen to me is still quite important. And knowing whether or not the outcome is predictable or not. The process of determining can something be predicted is actually quite valuable on its own, because we have access to a large amount of data, but not all outcomes are actually predictable. Many outcomes are not predictable. And if something is not predictable, then it gets us back to the situation where we need to treat every patient the same because we can't guess at what the outcome is. Knowing the situations where you can predict and knowing the situations where you can't predict, both of those have value. Because if we can't predict something, it should raise the question, what other data can we go collect to try to make this predictable? And if we can predict something, then we should start to use that information now and not worry about what other data might exist in the future. So, another example of prediction models in practice, we mentioned this maybe yesterday or 2 days ago, is predicting stroke in patients with atrial fibrillation. So many of you are going through your medical training. At some point, if you haven't already, you are going to learn about the CHADS-2 prediction score. They might not use the word prediction to describe it. They'll just tell you, use the CHADS-2 score. But this is the paper that originally was published to describe the CHADS-2 score. And it is very much a prediction model using observational data. Specifically, they took claims data from the United States, and they made a cohort of patients who had atrial fibrillation, and they used the medical history of the people before they had atrial fibrillation to predict which of those patients in the future got a stroke. Now, they did a very, very simple model. They only used 5 variables. They used congestive heart failure, hypertension, age, diabetes, and prior stroke. And what they did was they created this score, which is very simple, so simple that you can add it up on your fingers. You can look at a patient and you can think, does this person have heart failure? Do they have hypertension? Do they have age? Do they have diabetes? Do they have stroke? And you, on the basis of that, you can add up those scores and you get a number between 0 and 6. So 0 would be the score if your answer is no to all of these things. And 6 would be your score if your answer was yes to all of these things. And right now, this model is still actively used in medicine under the idea that if your score is more than 2, then that probably means it's a patient who we should think about giving anticoagulant treatment for, to reduce their risk of stroke. But if their score is less than 2, then maybe they're not risky enough such that we would have to be able to, that you don't necessarily have to treat them. So this is the idea that if we didn't have this model, every patient with atrial fibrillation would have to be treated the same. But because we have this model, we can use the score to decide which patients we're going to treat and which patients we're not going to treat. So the paper, as it describes it, talks about this scoring system that I just mentioned. And this model was based off of a sample of data of a couple thousand patients who had atrial fibrillation, and that's how they trained this model. So our question, claims data is one of the types of data that we could put into the OMOP common data model. So the question that you should be thinking about is, what data are required to create this cohort of patients with atrial fibrillation and to calculate this score, the CHADS-2 score, and to evaluate this outcome? And it turns out that there are 10 different pieces of data that we would need to look at in an observational database in order to apply this model. We, of course, need the variables that are in the model itself: congestive heart failure, hypertension, age, diabetes, and stroke. But we also need to be able to identify patients who have atrial fibrillation, because that's the population at risk. We need to be able to look as to whether or not those patients have warfarin, which is a drug, and specifically, we need to be able to look for the outcome, which is stroke. Now, Ling Yi presented to you the OMOP common data model, so you have seen this cartoon, and many of you said that you didn't quite fully understand it. So let me provide this example to give you a sense of how to use this data model. When we say we need the information heart failure, hypertension, diabetes, cerebrovascular disease, atrial fibrillation, those are all conditions, and so they're in our condition table. When we say we want age, that's a demographic, and it's in our person table. When we say we need a measurement, such as systolic blood pressure to find hypertension, or hemoglobin A1C to find diabetes, well, that's a measurement in our measurement table. If we want to look for warfarin, that's a drug in our drug table. If I want to know what kind of insurance a patient has, that's in our payer tables. If I need to find people who are discharged from the hospital, that's in our visit table. And if we have a composite rule like patients who are hospitalized for a stroke, well, then we can use information from 2 different tables. We can use the visit table to find the hospitalization. We can use the condition table to find the stroke, and combine those things together to find the outcome of interest. So the CHADS-2 prediction score fits our prediction framework perfectly fine. Your target cohort is patients who are newly diagnosed with atrial fibrillation. Your outcome is stroke. In their study, they looked 1,000 days out to find which patients had stroke. And their model specification was that they ran a logistic regression with 5 predictors, the 5 predictors that they chose. That is an example of a model specification, the type of statistic with the type of predictors that are used. Now, the CHADS-2 is a prediction model that actually is being used all around the world. The truth of the matter is the CHADS-2 prediction model is not very good. Its accuracy is actually pretty low. We're going to talk about a score, an area under a receiver operating characteristic curve, which is an ROC. And that's a measure of how well a prediction model works, where 0.5, an AUC of 0.5 is the equivalent of flipping a coin, so it is totally random guessing. And an AUC of 1 is a perfect prediction. The CHADS2 score has now been externally validated and shown that its predictive accuracy is only about like a 0.6 to a 0.65. It's a little bit better than random guessing. It's very, very far away from perfect. And yet, almost all of you who are becoming doctors are going to be told to use it to treat your patients, because being a little bit better than random guessing is a heck of a lot better than having nothing. Okay. So I want you to keep that in your mind, that many of you are already being trained to use a prediction model. You may or may not have known that it was trained on observational data, and you probably will never be told that its performance is not very good. But that's the truth of the matter of what we're using. So our question is, can we build prediction models, and can we do any better than these types of models that are already being used in clinical practice? Okay. So in the slides, we're providing you some references in case you do become interested in this prediction space. A recent paper that was published talked about the challenges in doing risk prediction in healthcare. And one of the things that they pointed out is that while the opportunity of developing prediction models in healthcare is a really exciting opportunity, the way people are going about trying to develop the models and write up their publications about them and then using them in practice is kind of not very well done. Specifically, some of the challenges that they cite is that people do inadequate internal validation, meaning they don't prove that the model is better than random guessing, or at least they don't do it correctly. The second problem that they highlight is that most studies use a small set of features. Just like the CHADS2 only picked 5 variables, the 5 variables for the CHADS2 turn out that they're a little bit better than guessing. But what if there were a different set of variables that would predict stroke even better? What if you chose a different set of 10 variables, and those different 10 variables did better than the original CHADS2? If that were the case, then it means that while we are doing something that's better than random, we might be doing something that's not as good as we could be doing. And maybe there's a better model for predicting stroke, but since we didn't learn it in the first place, every doctor has been taught the CHADS2 model, and that's just what we're using. The paper cites the fact that there's incomplete dissemination of models and results. So lots of people are publishing papers and saying, I learned a model, but then they don't actually tell you what the model is. And if I don't tell you what the model is, you can't use it in clinical practice. So we've got to be able to clearly describe exactly what is that model. If I train a model in one database, I have no idea whether it's going to work in a different place. If we learned a prediction model here at Fudan University, how do I know that it's going to work in my hospital at Columbia University? The challenge with that is that you have to be able to transport the model, take the model from here, and bring it to Columbia University where I can run it to see whether or not it works. This is also called external validation, to basically prove that the model works in different places. And the vast majority of the literature does not do adequate external validation. The main reason is because it's really, really hard, because different data are represented in different ways, and people don't collaborate with each other. And so you end up with the first paper published is a model trained here at Fudan, and then we say, hopefully this will work for everybody else. And then other researchers in other parts of the world read the paper, and they have to decide whether or not they want to try to implement it based only on what is described in the paper. That's very difficult to do. Part of what we've developed in OHDSI is the ability to take a model and actually share the code with someone else in the world so that they can run the model and see how well it works. The last comment that they make is that the impact on clinical decision making is unknown. So the CHADS2 model predicts stroke. But what we don't know is, did we actually improve patients' lives with atrial fibrillation by using the model? It's never actually been tested that we're doing the right thing by using this model in practice. And so for all of these reasons, the conclusion of this paper is that even though most people could agree that the idea of prediction sounds like a good idea, in practice, very, very few prediction models are actually used in clinical practice. And this is the problem that we're trying to overcome, because if it's the case that just doing a little bit better than random guessing could really improve patients' lives, then we should be able to do this at a much greater scale. So within OHDSI, we have a mission specifically focused on trying to advance patient-level prediction. And so our goal is to develop a systematic process that can learn and evaluate large-scale patient-level prediction models using observational data across a data network. So the work that I'm sharing with you today is actually the work of a large work group led by Jenna Reps at Janssen Research and Development and Peter Reinbeck at Erasmus MC in Rotterdam, Netherlands, who are leading a work group that are solving the scientific problem of how to do prediction in healthcare. And so what Kristin and I are sharing with you is really the work of a large group that's working in this space. So what we're going to talk about now is how to actually build and validate a prediction model. And so the steps that we are going to take is that we need to define a problem, we need to extract the data, we need to train the model, which means apply the algorithm to come up with those coefficients. We're going to internally validate the model, meaning we're going to see how well it works in one database. We're going to externally validate the model, which means we're going to test it somewhere else. And then we're going to disseminate the model, meaning we're going to write papers and provide access to these models to the world. The reason we spent 2 full days on the very first step is because it's by far the most important one. You've got to be able to define your problem correctly. And when we talk about defining a problem, we focused on thinking about coming up with a good clinical question, defining your T and your O. But it's also important that defining this also means producing documentation. We should write a study protocol that describes exactly what we're going to do through this process. It's very important to share that document because this is the only way that other researchers will know what you've done and can possibly follow your steps to do the process. And so what we're going to be doing today as part of the tool is producing documents, a protocol that we can communicate to the world of what we are doing, and we're going to be sharing that document and the code so that other people can do it with us. So data extraction. What actually happens here? Once you have defined your target cohort and your outcome cohort, as you saw yesterday with the use of the Atlas tool, we basically go into the database and just find the people who have the target or belong to the target cohort. We separately went and found the people who belong to the outcome cohort. And as you saw yesterday when we did our characterization, we could use those data sets to answer questions. Like yesterday, we summarized the people who have endometrial cancer, and we computed the incidence of how many of those patients with endometrial cancer had lymph node metastases. This data that's extracted can then be used to train the model. When we extract the data, what we have is all the people with endometrial cancer, and some of them are going to go on to have the outcome of lymph node metastases. But for purposes of training a model, what we're going to do is we're going to split the data set into two halves. There's going to be a half of the data that we're going to use for purposes of training the model. And then there's going to be a half of the data that we're going to use for purposes of testing our model. And the reason why we do this test train split of the data is because we want to be able to produce an honest estimate of how well the model works. And so we're going to use some of the data to learn a model, and we're going to separately use a different piece of data to see how well that model works. So when we talk about model training, there are many different algorithms in machine learning to train this type of a model. Basically, the prediction problem is amongst people who belong to your target cohort, use all of the variables in the past to predict some outcome in the future. That generic statement of a problem can be solved with many different types of algorithms. And I'll just highlight that within the OHDSI framework, we have implemented a large number of these different machine learning algorithms so that we can test and learn which ones work best. In terms of words that you might see when you read the literature, the most common thing that you'll see is people use a logistic regression. And a logistic regression is like that mathematical formula that I showed earlier. It's a linear combination of variables to produce a predicted probability. Other algorithms include random forest, which is basically an idea of partitioning the data into small subgroups, where the subgroups then might have different risks. We have other algorithms including gradient boosting machines, decision trees, neural networks. Some people may have heard this buzzword of deep learning, including recurrent neural nets. We have implemented many of these machine learning algorithms in the OHDSI framework. The point that I want to impress upon you, though, is that you don't have to know what the model is inside the black box. You just need to know that the black box is doing a good job of predicting your outcome. And we need to be able to test and verify that that model does a good job. So there is no magic answer to what's the right algorithm to choose. It's an empirical question, which is you choose whichever algorithm gets you the best performance. You choose the algorithm that maximizes your ability to predict the outcome. And so long as you focus on that, then all of these are reasonable alternatives to consider. It actually turns out that there's a lot of work and a lot of thought that goes into this, where people have been trying for many years to prove that one model is better. And it's now been determined that you just can't have one model that's going to be optimal in all circumstances. Instead, different situations are going to call for different techniques. And so what we recommend when you think about training a prediction problem is the following. You start with one algorithm. Today we'll start with logistic regression as an example of one. And you run your prediction problem using that one algorithm. And you're going to get an output which is going to be the performance of that model. And there will be two scenarios that could happen. Either you think the performance is good enough, in which case you should stop and report your results in your paper. Or you're going to think that the performance is not good enough and that you feel like you need to keep going. And if you need to keep going, then you can change the parameters of that algorithm to see whether or not that helps. And two things will happen. Either it does help, in which case you can stop and report your results. Or it might not help, in which case you could circle back and try yet another algorithm. You might find that it's not a model parameter problem, but it's actually the choice of predictors that you've made. And so if you find that the current set of predictors are not getting you adequate performance, you could change the predictors. You might also find that maybe changing the predictors doesn't help. So you might want to test your model on a different database. Because maybe one database does not have the right population of interest, but another one will. If you've tried every algorithm in every setting, in every predictor on every database, and you still can't predict your outcome, then probably you should change your prediction problem. Because what you've shown is you can't predict the outcome that you're interested in. But importantly, this idea of what is the right set of steps to get to an optimal model, this is a research area that has no solved solution yet. And so what we're actively working on in OHDSI is how to optimize this process. Today, for Bonnie's question, we're going to go through this process, and no matter what, we're going to report out our results. Because either we're going to learn that we can predict lymph node metastases, or we're going to learn that we can't. And both of those are valuable insights, whichever one that we find out. Okay, so on the roadmap, we're talking about evidence generation being the steps that you need to take to produce the model. And so the steps that we will need to do is we need to produce a protocol, we'll need to extract the data, we'll need to create the code that can actually train this model. The next step is actually going to be about evaluating the model. How do we prove that the model is actually doing better than random guessing? There are two main statistics, or types of statistics, that we're going to look at to prove that our prediction models are doing a good job. The first is discrimination. We want to be able to show that the model does a good job of separating people with the disease from people without the disease. And so discrimination is going to be our way of determining that we've got, that if I had two random people in front of me, one who had the disease and one who didn't have the disease, that I've got a better than 50-50 shot of getting those two people right. The second type of statistic that we're going to talk about is calibration. Because remember, the predicted probability, the output of a model is going to be a predicted probability. It's the likelihood that you have an outcome. Calibration is about making sure that those predicted probabilities that we produce are actually the right number. If I tell you that you have a 10% risk of something happening, we want to make sure that it's actually 10%. And so when we evaluate calibration, we're trying to make sure that the numbers that are produced by the model seem to actually be the numbers that are consistent with what will actually play out in the future. Okay. Yeah, that's a little messy. Let me see if I can. Okay. Yeah, actually, that's okay. So I'll try to explain this, and then we'll have this little video to try to explain this better. So every person is going to get a predicted probability. So think of my 1,000 people. Every person got a probability. But if you did know which of those people were the people who actually had the disease, and let's say we colored them in red, and we knew the people that didn't have the disease, and let's say we colored them in blue, then what that means is that you have a distribution of possible predicted probabilities for two groups. The probability for the people who actually got the outcome, and the probability for the people who didn't get the outcome. And so this picture here, imagine we had some prediction score where the people in blue represent the people who didn't have the outcome, and this is their probability score. And the people in red, that represents the distribution of probabilities for the people who did have the outcome. When we set a threshold, a predicted probability threshold, what we're doing is we're drawing a line through this plot. And this distribution then tells us which people are the true positives, the false positives, the true negatives, and the false negatives. And this table that we showed earlier is the table we're going to use to understand how well our model actually works. Because you have the prediction of who's predicted to have the outcome and not, and the actual truth of who did have the outcome or not. So let's see if this works. So you can see that if I drag the line to the left, this plot that I'm showing you here is the area under the receiver operating characteristic curve. The y-axis is sensitivity. The x-axis is specificity. And so as I move that line, I'm moving the threshold of that trade-off between sensitivity and specificity. The closer that those probabilities are together, the worse that this area under the ROC curve represents. So if we cannot separate the predicted probabilities from those who have the disease from those that don't, then we will be no better than random guessing. But if it's very clear that all the people who have the disease have a high probability and all the people who don't have the disease have a really low probability, then we have very good discrimination. Does that make sense at all? No, I see a couple head nods, so okay. So the idea of discrimination is we just want to know how well we can do of separating the people with the disease from the people without the disease. Calibration is making sure that the predicted probability we give every patient actually reflects the observed risk that that patient is going to experience. Actually. So I'll just show it as this. So imagine in this plot, I'm showing you the predicted probability on the x-axis and the observed frequency of the event on the y-axis. If a model is well calibrated, then whatever you predict to be the outcome should be the probability that they experience the outcome. So you should be directly on the 45-degree line, which is represented by the dashed line there. When we apply a prediction model, we can actually evaluate, are we actually producing the right probability, or are we sometimes underestimating the risk or overestimating the risk? And if we learn that we have a model that is miscalibrated, meaning it's not producing the right predicted probability, the good news is that there's a mathematical way we can fix it. If you produce a probability that's lower, we can just bump it up by the right amount so that it gets to the right value. But you can only do that if you know that you first measure the calibration of your algorithm. All right. So we've just done internal validation, which is how well did your model work in your own data. The opportunity is to do external validation, which is to take the model from one place and apply it to database somewhere else. And this is probably the most substantial opportunity within the OHDSI community, is that we don't have access to just one database. We have 100 databases around the world that are possibly available to do this type of validation activity. So when we train a model in one database today to determine the risk of lymph node metastases in patients with endometrial cancer, the reason we're going to know that we've got a good model is because we will be able to see how well it works in other databases around the world. And then last but not least is dissemination. Once we build a model and we learn that it works, we've got to figure out how to communicate this to the world. So the reason we've been talking a lot about publishing papers is because publishing papers is one way to disseminate evidence. And it turns out that there is reporting guidelines for how to write good papers for prediction. That didn't seem like it really helped. It just shifted it the other way. there is already a recommendation for how to publish prediction papers. It tells you what pieces of information should be in your paper. It's this document called the tripod statement. So if you all are interested in writing a paper on prediction, all you have to do is follow the steps of the tripod statement, which tells you what to write in your paper. And so when we write our papers in OHDSI for prediction, we follow the tripod statement, we follow what it asks for, and then we know we have disseminated everything that you need to be a good paper. Publishing a paper, which is fine and good to do, is one way of disseminating, but it's important to highlight that that is only one way. You can also disseminate your models in other ways. One of the things that we've done in the OHDSI community is we share all of the material that we produce on the OHDSI website. And that includes sharing the models themselves through interactive websites where people can go explore the results of a model themselves and not have to read a paper in order to understand what's been done. This is the reference to the tripod statement. A lot of researchers around the world got together to write this document of the right way to publish prediction studies. And so we think it's actually a useful framework that you should all follow. Okay, we're at 10:30. We go to 11:30. I think actually we'll go through this section. Okay. So I want to provide an example of prediction work that we have done in the OHDSI community to help you bring all of these different pieces together and understand why this is important. And raise your hand if you did your homework and read the paper we sent out yesterday. The paper in Jamia by Repsodol. Some people, a few people read it. Okay, that's all right. So I want to talk a little bit about the results that are in that paper because I think this should help you think about your own prediction problems. So the problem that we were interested in was patients who are pharmaceutically treated for their depression. So think of any patient who's got depression who's actually getting a drug for their disease. And the question that often comes up for those patients is that they are worried about the risk of different side effects because antidepressant drugs on their product labels have a large list of known side effects. They have a black box warning that says that there's the increased risk of suicidal behavior. They have many other side effects that are well known that patients are worried about. And so our objective was to determine whether or not we can predict any of the outcomes that occur in patients who start treatment for their depression. And so the way that we defined our prediction problem was we found patients at the time they were first treated for their depression, and that became our index date. We used their entire medical history before that date to look 1 year into the future to predict 22 different outcomes. And in that paper that we showed the results for, we ran our analysis against 4 different databases. And we actually applied multiple different machine learning algorithms to those prediction problems to see how well we could do. And we used as predictors those patients' demographics, their conditions, and their drugs to see what we could learn. So we defined our target cohort as patients who had a first occurrence of pharmaceutically treated depression. It meant that these patients had to be in the database for at least 1 year before the time that they took their first drug. They had to stay in the database for at least a year or have the outcome of interest. And we required that they not have the outcome before they entered into the cohort because we were only looking for the first occurrence of the outcome. So here's some details about this study. Our 4 different databases represented different populations in the United States. These were very, very large databases covering over, I don't know, over 1 million patients with depression in the world. So we extracted all of the data. We did a test train split of the data, and then we evaluated how well our models trained for in one database applied to other databases. We applied 3 different algorithms: gradient boosting, random forest, and logistic regression. And here were all of the outcomes that we predicted. And these are a wide range of different types of clinical situations, from very rare events like acute liver injury to very common events like diarrhea. Some of these events were very, very serious, like a heart attack. Some of them are more like nuisance effects, like nausea. But our goal was to determine, can we predict any of these outcomes for these patients, since they all might matter. So just to highlight as an example, if I look at stroke across our database, we had thousands of patients who experienced a stroke after being depressed. And so the prediction problem that we would be tackling is amongst, take this top database, CCAE, amongst the 600,000 patients in our target group, can we predict the 1,300 patients who go on to have stroke in the next year? That was the prediction problem for that one example. And so I'm going to orient you to this picture so that you can interpret these results for yourself. What you're seeing is on the x-axis, we've lined up all of those 22 different outcomes. And these colored bars here represent the 4 different databases. And inside of each database, you're going to see 3 rows representing the 3 different algorithms that we ran. And so I'm just showing you now one color, which is stroke, one column, which is the outcome of stroke. And I've color-coded the performance from red is an AUC of 0.5, meaning it's no better than random guessing. So we wouldn't probably use that in clinical practice. All the way up to blue, which would be a perfect model, that we can totally know exactly what's going to happen to every single person. Okay? So the question that we had was, how well can we predict these 22 outcomes across these databases for these patients with depression? And for stroke, you could see that in 3 out of the 4 databases, we were green. So we got area under the curve of greater than 0.8, which is pretty darn good. We could actually do a pretty good job of predicting who's going to get a stroke and who's not going to get a stroke in the next year. Now remember, does anybody remember how well I told you the CHADS-2 score works? Remember what value I told you the AUC? 0.65. So the CHADS-2 score, which is a model to predict stroke, only gets an AUC of 0.65. But when we applied our methods to our data, we got an AUC of 0.8, meaning we could predict stroke better than the CHADS-2 score can predict stroke. Now you notice 3 databases were in the green. 1 database was kind of in the yellow. That's an AUC of about 0.7. And what's interesting that we learned is that different databases perform differently for the performance of these models. And that's really important because good time to open that up, yes. So that's really important because most prediction studies that have been published only ever evaluate on one database. And you have no idea how well it will work on a different database. Here, we were able to look at the performance on 4 databases all at the same time to understand its performance. So, what did we see? Across all of those outcomes and all of those databases, So the columns were the different outcomes. What you could see was there's an awful lot of green. There are a lot of different outcomes that we could successfully predict which patients were going to experience those outcomes. Quite a lot, actually. But we also learned that there were some outcomes that we could not predict so well, that are in the orange. And I would actually say it's valuable to learn that we couldn't predict certain things, because that tells us which information we should be using and which information we should not. So one of the things that we learned was we could look at the different databases. And we saw that different databases exhibit different performance. In this case, we learned that it was harder to train models in this database than other databases. And that might give us insights to explore that space further. We saw some outcomes we were really pretty good at predicting. Myocardial infarction. We're really good at predicting who's going to have a heart attack in the next year. Hypothyroidism. We can actually figure out who's going to have hypothyroidism. Stroke. We can predict stroke. We have a really hard time predicting who's going to get diarrhea and nausea. Our data don't necessarily support those prediction problems. If I just limit myself to the outcomes where we get an AUC greater than 0.75, which would generally be considered to be a pretty darn good model, you can see that there are a lot of circumstances where we could help patients with depression simply by using these models to provide predicted probabilities. And if a patient came to you as an aspiring clinician and said, "What's going to happen to me?" these are models that you should feel comfortable using to be able to tell these patients, here's your probability of having a myocardial infarction. Here's your probability of having hypotension. Here's your probability of having a seizure. Here's your probability of having a suicidal event. And that would be a lot better than doing nothing, which is what we currently do. Now, what we also learned that was methodologically interesting is that there are some situations where the choice of the algorithm didn't matter at all. And then there were other situations where the choice of the algorithm did matter. And it was not always the case that one algorithm was better, or it was that different algorithms performed differently in different circumstances. That paper that I asked you to read, the reason to actually highlight that is one paper published that tackled one disease for 22 different outcomes, so it's a very large paper, but it showed what's possible in applying prediction in a way that can really make a difference. What we need to do is do that same thing, not just for depression, but for all of the disease areas that you all will be treating your patients for, so that you can have that information available to support your patients. So, what have we achieved in the OHDSI community so far? Oh, I'm going to ignore Jenna. There's our very own Jenna, who's now pinging me. So, we want to have adequate internal validation. We now have a best practice to follow for that. We have a full data-driven approach that we have. So we are going to go through now in Atlas how we can actually design a study and run it. And that process is following our scientific best practices. We have a process for disseminating the models and the results that's available. And we've created the ability to transport models across the world. What we haven't done is evaluated the impact on clinical decision making. I believe it's a good idea to apply prediction models to healthcare, And many people also believe this, and there's lots of papers that are excited about this idea. But we still need, as a research community, to prove it by demonstrating that we're actually improving the lives of patients through the use of these models. And that's the opportunity that's actually in front of us. So that paper that we showed, this is an important paper that we've published in the community. But everything that we're going to go on, that didn't come out very well in the middle of that. That looks awful. Everything that you're going to see for the rest of the day is all publicly available on the OHDSI website. As Kristin showed, the Book of OHDSI has tutorials for how to actually follow this process that you read about in the paper, and all of our results are publicly available. What we're going to do this for the rest of this morning and this afternoon is actually dive into doing one study, which will be Bonnie's study of endometrial cancer, following the best practices that are followed. But I would strongly encourage all of you to think about prediction questions that you think are important, like the ones we wrote down on the board, and encourage you to think about doing your own research in the OHDSI community to explore those questions. All right, so that. So with that, we're going to, in the next 45 minutes, design a prediction study. And encourage all of you, if you want to follow along, we're going to be using Atlas again. So go ahead and log into Atlas. What happened to my screen? Hello? Okay. Just decided to take a. Yes. Yeah. No. Okay. So I encourage all of you to log in to Atlas. You got your username and password as we did yesterday. Make this a little bit smaller. So, what we're going to do is walk through the process of designing a prediction study. That's what we're going to do before lunch. And then this afternoon, we are going to actually execute our design, generate results, and write a paper. So, the first part is that we just need to answer some simple questions about what models that we want to choose and what predictors we want to use. So I'm going to be designing this study for Bonnie's question, but if you have your own question or want to follow along, feel free to do so. All right, on the left-hand side, you will actually see that there is an option called prediction. And that's what we're going to do. We're going to design a prediction study. I'm going to start a new prediction patient-level prediction, which is going to be Fudan tutorial, Bonnie's prediction question, which is predicting lymph node metastases in patients with endometrial cancer. All right. So, I did a lot of talking there. You're going to see on this form that there's not actually a lot that we have to do to decide on a prediction study. Very specifically, as you probably should hopefully expect by now, the tool is going to ask you, what is your target cohort? And so we are going to add a target cohort, which will be our patients with endometrial cancer who had those additional inclusion criteria. We then need to select our outcome cohort, which I think we said was secondary malignant neoplasm of the lymph node. From there, we need to now we're getting into the model specification, which was that part that we didn't talk about so much yesterday. So what choices do we have to make? Well, the first is that we can choose from any collection of different machine learning algorithms that are available to us. So we discussed, for example, we could run a logistic regression, and we can simply select that from the list. When you click on that, it will bring you up to a screen that will list one or more parameters of the machine learning algorithm. These parameters are things that statisticians and data scientists may decide to play with, but by and large, we have created a recommended set of default values, which are what you should use. If you don't understand what these are, just use the recommended values and you'll probably be in good shape. So here we can see that the hyperparameter for the regularized regression is 0.01. That's a perfectly fine value. So you can see there we have now selected the algorithm that we wanted. Note, if I wanted to select a different algorithm to also run, I could select that. So I could select, for example, random forest. And here you can see random forest has a different set of parameters that become available. Excuse me. And so now you can see in my analysis, for my one target and my one outcome, I've selected two different algorithms that I could run. The next set of choices that I have to make are the covariates, or the predictors. Which variables do we want to use to try to predict from the past medical history the outcome in the future? And so I can click on my covariate settings, and we can see that automatically we have a large number of choices that we can use for our prediction. So let's go through these one by one, and we'll actually, Bonnie, I'll ask you questions as we go, but I want you all to be thinking about this. So, do we want to use gender as a predictor of our study? No, we don't probably need gender because everybody's female. So we don't need to have that. Would we like to use age as a predictor? Yes. Now here you can see there's actually two different ways to use age. One is to use age as a continuous value, so your actual age that you would have. And the other is to use age groups. So basically splitting people into 5-year age buckets. There's no right way to do this, but the distinction is if you use age as a single continuous variable, you are assuming that there is some sort of a linear risk. The older you get, the higher your risk is, or lower your risk might be. But when you use age groups, you can allow for a non-linear risk that could exist. Here, since we don't really know, I would say we could just include both and see what happens. Do we think race might influence our probability of having the outcome? Yes. Okay. And ethnicity, which actually Christian was explaining to me this. So in this context, we are forced to use standards that might not make sense here in China. So I should probably be clear about this. Race is, think of that as your country of origin. And ethnicity in this case is a classification as to whether or not you are Hispanic. So in this case, these might be information that might differentiate a risk. Here I've selected index month. So do you think that it's possible that the month that you are diagnosed with endometrial cancer might possibly in some way predict the outcome of having lymph node metastases? That's right. Very good. Yeah. So if we don't know, our default thinking here, that's an excellent answer. If we don't know, then default should be let's try it, because there's no reason for us to presume that we know that there's an effect or not. If we don't know, we could include it. The only time that we would probably want to remove something would be like gender. We know everybody's female, so that doesn't make any sense to include in. So we can consider whether or not calendar time is going to matter. All right, I'm going to scroll down here. So now we have in our in the common data model as Lingyi presented, you had different tables of data. Every one of those tables represents information that we could use as a predictor. So for example, conditions. Do we think we might want to use other medical diagnoses as predictors of future cancer? I think that probably makes sense. Now, we have a second question that we have to ask. If we're going to use conditions, we have to decide how do we want to create the predictors in relation to time. We have an index date, which is the date that you have your endometrial cancer. So do we want to look for conditions that are very close in time to that date? Or do we want to look for conditions that are very, very far back in someone's medical history? Or do we possibly want to use both? We get the choice of both whether or not to use conditions and what time windows do we want to look at. So I guess to use this as the example, would you like to use everyone's full medical history as one possible predictor? Yep, okay, that sounds good. Would you also like to use only the things that happen very, very close to the endometrial cancer? Yep, we can use that too, okay? So here what you can see I've selected all time prior, so that's going to use the whole medical history, and I've also selected a short-term window of 30 days. That means that for every single disease, diabetes and hypertension and heart failure and other cancers and whatever it might be, for every single disease, there are now going to be two predictor variables. One predictor variable says, did I have diabetes ever in my medical history? And the second one's going to be, did I have diabetes in the last 30 days? Those are going to be two different predictors for the same disease for every possible disease. Okay. Would you like to use which drugs a patient has taken in their past medical history? Yep, okay. Would you like to use all the drugs in their medical history or just the ones recently? All time in history? Okay, very good. Do you think that it would matter the specific drugs in the short time, or probably just using all of their drugs would be good enough? And the short time? Okay, very good. This one I'm going to deselect, but I'll explain what this is. You could also think in some prediction questions about whether or not a person is on a drug at the exact moment of the index date. For your problem, I don't think that this necessarily makes sense, but there are other situations, particularly if our target cohort was based off of an exposure, that you might care about whether another thing was also exposed at the exact same time. So polypharmacy, for example, that's why this option's there. Doesn't make much sense in your context. Okay, so we're going to use conditions and drugs as one domain of information. Do you think that the procedures that a patient has undergone would matter? So if they've had prior surgeries, for example. Yeah, that would matter, okay. Do you think that you want to know their medical history of all the surgeries they've had in the past, or just surgeries they've had just recently? Mm-hmm. Yep. So would you like to do both, their whole history or just recent? Okay, instead of the short. Good. Yep. So those are procedures. Now, we also have measurements, so the laboratory test values that we would have. Now, there's two types of measurements to think about. There's the fact that a doctor asked for a measurement. We don't know the value. You don't have the value of it, you just know that a measurement took place. And then there's the values itself. The reason these are separate ideas is because some databases don't actually contain laboratory values. They only contain the fact that a measurement took place. It turns out, knowing that someone got a measurement turns out to be a pretty powerful predictor sometimes. Because the only time that a patient gets a measurement is if a doctor suspected there was something wrong and ordered a measurement. So that's why it makes for a good predictor, even if you don't know what the value is. So, question to you would be, do you think laboratory measurements is something that we might want to use? Yep, okay. And would we like to use as predictors just that measurements have been ordered, or do we want to use values, or possibly both? Both? Okay, very good. Probably with measurements, well, I'll say more generally. Measurement values are a tricky piece of information because patients' measurements change over time. So this is often a situation where people might want to only limit themselves to recent measurement values, because having a measurement value from 2 years ago probably isn't indicative of your current health state. Does that make sense? So like if we're thinking about cancer indicators, you care about what happened in the last 30 days a lot more than you would care about if you were worked up for cancer 5 years ago. So we could use values from the last 30 days, but maybe we'll use the fact that measurements at least were measured in the past as another predictor. Just for purposes of completeness, we'll just highlight there are other types of domains of information. Actually, maybe possibly using measurement could be useful here. So observation is kind of our catch-all that Lingyi presented about. We have things like possibly smoking status can be in there, or family history information possibly is in there. So there can be some observations. You can also have devices that have been a patient is exposed to. So, for example, if someone had a hip replacement, for example, the fact that there's a hip implanted could be the kind of a device that you'd have. So for devices, do you think that that matters at all? Is there any devices associated with endometrial cancer? Yep, IUD, perfect. Okay, good. So I'll put devices anytime prior, and that would get to the IUD. That's a very good one. Yep, excellent. Okay. So for everything we just described, these are going to be predictors, which basically is asking the question, do we observe this data in this time window, yes or no? It's based on the absence or presence of this information. We can also have variables that are count variables. For example, the number of times that you visited the doctor in the last year, which sometimes could be a predictor of the fact that people who go to the doctor more often are different than people who don't go to the doctor more often. So do you think how many times you go to the doctor might predict, could possibly predict lymph node metastases? Possibly? Okay. You also have the ability to create those same kind of count variables for number of conditions and number of drugs and number of procedures. So you can think about the density of that. Of course, we're already selecting the individual variables, so we're probably pretty well covered there. You also have the ability to create predictors which represent risk scores that are already known. So for example, I highlighted the CHADS-2 score. That's something that everybody uses. You could actually include the CHADS-2 risk score in your own risk score if you thought that that was important. These might be important if your outcome of interest has anything to do with these things. Probably less important if you're doing something very different. So the CHADS-2 is a risk score for stroke. Does it have anything to do with cancer? Okay, so maybe we'll take those off. This next one here is the diabetic complication severity score. So it basically is how bad is your diabetes. Do you think that that might impact cancer? Possibly, okay. And the last one here is the Charlson Index, and this is a probability of death. So do you think how sick you are and how close to death you are might impact cancer? Possibly, okay. So this process of selecting covariates that we've just done, that is the process of picking your covariates. And so we've selected a whole bunch of them there, and they're shown on the screen. Importantly, as a general principle, we don't think that what you should do is cherry pick your 5 or 10 variables. Instead, you should think about what domains of data might be important, and also think about what databases you're going to be using to train your model. So the reason that we might keep or drop a domain of data isn't because we think it's a good piece of data or not. It might just be because we know that the data we want to use doesn't have it. So we'll use what Bonnie selected here to train our model, but as we move forward, we might consider that if one of these domains limits the choices of databases we have, then we might remove those since they will not be available to us. Okay. The next section is population settings. So here is where we have to define our time at risk. So Bonnie, yesterday we talked about that we were interested in a 1-year window and then also possibly a 3-year window. And we talked a little bit about how I said we were going to talk a little bit about how does the time at risk truly start. Because you've got a date where you have the endometrial cancer, and then we're going to have a date when the lymph node metastasis happens. So if I saw a lymph node metastasis happen the day after the endometrial cancer, my question that I asked yesterday was like, do we really think that that's the outcome that we're interested in? And I think the reason being that if two things happen really close to each other, it's probably not that they happened in sequence, but rather they really existed at the same time. So one way to resolve that issue, if we don't want that situation, is to define our time at risk to start a little bit after the index date. So here, just as an illustration, we're saying the time at risk is from 1 day after the endometrial cancer to 365 days after. But if we don't want those outcomes that happen right at the same time, we could just change this time window. So for example, we could say something like, I'll just pick a value at random. We'll start the time at risk a month later, because inside of a month, maybe we don't believe that that's really a new outcome, but after a month, maybe it's possible that something new is happening. So a question to you, Bonnie, would be I'm picking that at random, but What do you want your time at risk to be for your study?
During time of
2 weeks? Okay. So you would have your visit for your endometrial cancer, and you'd have some like follow-up after 2 weeks. Okay. So we could just set that to 14 days then. Okay? Okay. Now, one of the settings that we have to decide is what is the minimum amount of time that someone has to belong to the target cohort in order to enter this prediction study. So remember, our target cohort itself requires people to be in the database for 1 year. But for purposes of prediction, we could require even more than a year. The real question becomes one of how much data do you feel like you need in order to train your prediction model? So the question to you, Bonnie, is right now we've got a year. Do you feel like you want to require more time than a year, or do you want to start by just using 1 year as our prediction time? Or a year. Okay, very good. So now there's, let's see, I'm gonna try to explain this, and if not, I might need to raise the, actually, you know what, I'm gonna try something, I'm gonna be daring here. I did it myself, good for me. All right, I'm gonna let that still be projected onto the whiteboard so you can kind of see it, but I'm going to explain the next question. The next question states, should subjects without the time at risk be removed? And the option is yes or no, and what is the minimum time at risk? So let me just draw a figure for you to understand what our problem is. We have, let me break the chalk here. All right. We have a moment which this person has endometrial cancer. And we know that this person is going to be in the database for at least 365 days, because that's what we've specified as our rule. And we've defined our time at risk, oops, shouldn't have drawn it right there, I should have done it right there. Our time at risk is now from 14 days to 365 days. Meaning this is the window of time where we're going to look for an outcome of lymph node metastases. And we're going to assign everybody to they either are going to have the outcome, either they have the outcome in this window or they don't. That's our prediction problem right now. But there's a little bit of a tricky situation that could arise. What if there's a person in our target cohort who leaves the database at, say, at day, I'll make up a number, day 100. So at day 100, they are out of the database. What it means is, up until day 100, I have not observed an outcome for that person, and now they're gone. Since they're gone, I don't know what happens to them in the future, because they've left the database. If I did see the future, I might see that that person had the outcome, but I don't get to know that piece of information. When I train my prediction model, I need to know how to handle this person. And I've got a couple options. Option one, I allow this person to be in my study, But since I don't see an outcome, I assume that the outcome didn't happen. That is, I assign this person to not have I assign the person as outcome equals no, meaning that since I don't know that this happened, I just have to assume it didn't happen. That is one option that I have. The advantage of that is that this person gets to stay in my study, and probably more times than not, I'm going to guess right that they didn't have the outcome in this remaining censored time. The other option that we have, though, is we could say, since this person didn't make it the whole time, let's exclude them from the study entirely. Since we don't know whether or not they had the outcome, let's just kick this person out of our study entirely. The downside of kicking them out is that you lose the sample that you have, but you do now probably have greater confidence that you get the outcome classification correct. This choice of what to do when people have incomplete follow-up time represents two different biases in your model. Neither are right or wrong, they're just different. But you have to make a choice about this when designing your study because it'll impact which data goes into your model. Does that generally just kind of make sense as an idea? Okay. So for your problem, Bonnie, for this specific situation, how would you like to handle this? Would we like to require that people are in the data for the whole time or some amount of time, or do you want to kick them out because they don't make it all the way?
I want to kick them out because we have enough sample.
Okay. So what I could do is I could say, should subjects without time at risk be removed? We could say yes. And we can say that they must be in there for the whole time at risk, which in this case is going to be 350 days. Okay. Which is to say, I'm going to require that someone makes it this whole time. So this is my minimum required time. I'm going to require that they be in there the whole time to keep them. Okay. Again, not right or wrong, but there's a choice to get to make. Now, you've just required that everybody makes it a whole year. But let's think about the people who have the outcome. These are people who are going to get a lymph node metastasis, which also means that they basically have serious extra cancer. Unfortunately, getting lots of extra cancer is bad. You might die. And so maybe patients don't make it a whole year. So what do we want to do in the situation? So now I'm going to erase my dashed line. What do we want to do in the situation where we observe that a person has the outcome, but then they leave the database? So this person doesn't make it a whole year, maybe because they had the outcome and then they died, right? So that's a possible, or they left the database. Let's be more favorable than that. So if that were to happen, a question becomes, how do you want to handle that person? Because since they've already had the outcome, you already know that you're going to call them a yes, even though they didn't make it the full time. So the question that the form asks you is, do you want to include people who've had the outcome who were not observed for the whole time at risk? And you're saying yes in your case. Let's keep this person even though they didn't make it the whole time. So in your scenario, we're basically saying we'll take all the outcomes that we observe, but for the people who are the non-outcomes, we're going to require that they make it the whole time. So that's perfectly valid choices to make. Fully support it. But just to be clear for everybody's benefit, those are choices that you have to make, and there is no right or wrong choices. It is totally rational to require a minimum time at risk, And it's also totally rational to not require it. In fact, I'm actively working on a publication right now with GeneReps that is focused on testing what is the consequence of this choice that you're making. Because we know it's important, but we don't know whether or not we can make a recommendation of the right way to handle it every time. Okay. The next, okay, so now I'm going to try this. There we go. Okay. Oh, that's going to go slow, so I'm going to do one quickly while that's going down. There's another scenario that could play out, which is, what if a person had the outcome before they entered the cohort? So in this case, what if a person had a lymph node metastases before they got endometrial cancer? How would you want to handle that situation? In our specific example, this is not applicable because we had an inclusion criteria that kicked them out. But in general, this is an important situation to think about is, do you want to kick out people who've had a prior outcome, or do you want to allow them to stay in the database and have a future outcome? Okay. So the next two questions turn out that they're not applicable to Bonnie's situation because of the definition of the cohort, but I'll explain them both so that you understand it. Should only the first exposure per subject be included? Meaning, if you enter the target cohort multiple times, do you want to be considered multiple times, or should we only use the first time? In your case, you can only enter the target cohort once, so this question is not applicable. But of course, you will only enter in once, and so you can only have a first time of endometrial cancer once, so it's not applicable. But if we were studying drugs, then you could have a drug, stop a drug, start it again, and those would be multiple episodes. And then the next one was what we just described. Should we remove subjects who were observed to have the outcome prior to cohort entry? So in this case, we would say, do we want to get rid of people who previously had a lymph node metastases? In this case, it shouldn't happen, so it doesn't matter. But just to illustrate the point, we could say, yes, let's kick out people with the prior outcome. And then you get an extra question, which is, how far back do we have to look to observe the prior outcome? Okay? All right. So we have now just defined a study that's going to look at a 14-day window to a 365 days. We're going to require a full amount of time, and this is going to be our population of interest. Now, Bonnie also was interested in studying 3-year risk. Yep. So we can create multiple settings to allow that to be done. So we're going to say include yes, yes, yes. And you can now see that we are going to have 2 different population settings. We're going to do a 1-year risk window and a 3-year risk window. The next set of parameters in the form are probably less interesting for everybody here, but I'll just explain them briefly. We can decide whether or not we want to sample our data when trying to fit a model. So sometimes our data is so big that we don't actually need to use all of it. And so we could say, for example, let's train our model by sampling only the top 100,000 patients. So if I didn't know going into this how many people we had with endometrial cancer, I might just train a model based on the first 100,000 people I find. We can also decide how to reduce the number of covariates we use based on their prevalence. the training settings. This decides how we are going to create our test train split. And so we can say, for example, I'm going to split the data based on persons. I'm going to use 25% of my data in the test set, which means 75% of my data will be used to train the model. And then these last parameters are really just about how we're ensuring that we do a good job with internal validation. So that is how we specify our analysis. If you go to the Utilities tab, what you'll actually see is you'll be able to review all the decisions that you made to run this study. And you can actually see what's interesting is it tells you how many different studies are we actually going to run. And you can see here, it's now saying we're about to train 4 models. So why do we have 4 models? Well, remember, we selected 2 different algorithms, logistic regression and random forest, and we're doing 2 different time windows, 1 year and 3 years. So that's why we've got 4 different combinations that we're going to study. The value of this structure is that we could have studied many different target cohorts, many different outcome cohorts, many different time at risks. But by applying the same consistent approach, we can combine that together into one analysis. So, Bonnie, you've just designed your first patient-level prediction study. And in fact, if I just save this as Bonnie's study and I download it, you can see popping up on my screen here is a zip file of files. And that zip file contains all of the code to run Bonnie's study. So now, by designing Bonnie's study in this way, I have the piece of code that I can send to anyone in the world. They can now run this code, train a model, and see how well their model performs. And so after lunch, what we're going to do is we're going to run this model on real data. We're going to look at the results of the model, and we're going to interpret to see whether or not we've done better than random guessing, and whether or not we can actually create some sort of a black box model that we think we could use to help patients understand which patients are at higher risk of getting lymph node metastases and which ones are not. Okay. So our task at this afternoon when we get back is we will look at running this code, seeing what outputs there are, and then we still have this pesky task that we still have to write a paper. We're running out of time. I think Bonnie's getting a little bit nervous. So this afternoon we'll go through exactly what it takes for us to take these results and write up a paper. All right? So I will see you guys at, what time is it again? 1:30? 1:30? I'll see you all back here at 1:30.